So in our test hypothesis journey so far, we've identified the test that we want to conduct. We've calculated a test statistic, or better yet, we've had software calculate a test statistic for us. And sometimes we saw that that was an easy number to evaluate, and other times it's not. And so the third step is, how do we evaluate a test statistic if it's not easy, if it's not one of those, what did I refer to them as, gimmies in the last video or in the last lecture? So we need a technique, we need a method, and the method that we use, the first method I'm going to talk about, is really based upon the journey we've been on. We know that if the null hypothesis is true, the value of the test statistic should be something we're familiar with. And so far we've looked at normal distributions, we've looked at t-distributions. So if we're working with one of those, we know what to expect. We know where normal distributions, we know where t-distribution should fall. Later on, the test statistic will change. It'll become an f distribution or a chi-square distribution. And there's a whole host of things that you will grow into as you run with this test hypothesis topic. But for the short term, for this conversation, let's assume we're working with a large sample. Let's assume we have a normal distribution. And here's what we know. When we work with test statistics, if we were to repeatedly sample, what did we say in the last video? If we were to repeatedly sample, they would form a z-distribution, not just a normal distribution, not just any normal distribution, but a z-distribution. That's the normal distribution where there's a mean of 0 and a standard deviation of 1. And so we know what to expect with that. So the first thing I'm going to say is, let's use that knowledge. The first technique we have for evaluating a test statistic, trying to get my animation to work here, all right, are the rejection regions. So the rejection regions gives value to the test statistic that are unexpected and lead us to reject H naught. If the null hypothesis is true, we should see a z value. We should see something that comes from a standard normal distribution. And you see I have written here, it's based on the sampling distribution of the test statistic, the direction of the test, and our choice of alpha. Just real generally, where do you expect to see things in a z-distribution fall? Between plus and minus 2? That's going back to what? The empirical rule from very early on this semester, right? For mound-shaped symmetric distributions, we expect most things to fall within 2 standard deviations of the mean. We've gotten more sophisticated than that. And with the test hypothesis, we can get even more sophisticated. With confidence intervals, we were looking at upper and lower bounds. And we took that 95%, we took it a little bit more seriously, and we didn't use plus or minus 2, we used plus or minus 1.96. Now, we have the ability to just look in one direction or the other. We have the ability to change our choice of alpha, which is directly tied to our reliability level. You may have heard my dog in the background. She was upset about the reliability level. So we have the ability to change that. We can go any value of alpha between 0.01 and 0.10. That's going to correlate to a confidence level of 90 to 99%. You get to choose. Now sometimes, especially if we're in a multiple choice testing environment, I'll choose for you, but you get the idea. So I want to do an example. In the example we're looking at, let's assume, where's my pen? I always lose my pen. Let's assume, let's draw a normal distribution here. And let's assume we have a large sample, so this will be a z-distribution. So I'll label this as a z-distribution. There we go. Let's assume we have an alternative hypothesis where we're testing, let's say, the mean is supposed to be mu is greater than 50. So we're doing an upper tail test. And let's say we want to use, in the example here, we want to use an alpha of 0.05. So what we're going to do is we're going to come to the z-distribution, which we know is centered here at 0, and we have an alpha of 0.05 to work with. Well, if we were working with two tails, we would put some of that alpha in the upper tail, and we'd put some of it in the lower tail over here on the left. But in the one-tailed test, where we're just looking upper tail, we're going to go and put all 0.05 in one tail. And we're going to try to find this value. We call this the critical value or the tabled value, the value of the z-distribution that has 0.05 above it. And we've seen a couple of different ways of getting this value this semester. We could go to a cumulative normal table and look up the probability. What's the probability below the z-naught? Well, over here it's going to be 0.9500. We could look that up in the cumulative normal table and find it, or we could go to, say, something like Excel and use the normal inverse function, put in a probability of 0.9500, put in a mean of 0, put in a standard deviation of 1. So we have a couple different ways of getting it, but that's where this 1.645 number comes from, either from the table or from the norm.inverse function in Excel. And what we're saying there is that if the null hypothesis is true, we should see something below that. We should see a value close to 0, and we expect our test statistic to fall below that z-value, that 1.645. And so what we're suggesting here is that if we see a test statistic bigger than that, that's going to support the alternative. In fact, that's going to be enough evidence to suggest that the alternative is true. Because if the null is true, it's very unlikely we'd see a test statistic out there. Now, could we be wrong? Sure, we could be wrong. But that's the way these inferential techniques work. There's always a chance of us being right. There's always a chance of us being wrong. In confidence intervals, we specify our reliability level. And we want to talk about the probability of us being right, or the chance of us being right, the percentage of the intervals that capture the mean. In test hypothesis, we float that around and we talk about our error rate. And that's the 0.05 in this case. So if I had a large sample, and a large sample when we're working with means, this would be n greater than or equal to 30. Right, that's our sample size criteria for means, which I always will remind you, it's not the sample size criteria for proportions, but it does work for means. And we had an upper tail test. That's what the rejection region would look like. What if it was a less than test? Well, then everything flips around to the other side of the curve, and we reject h naught of z as less than a negative 1.645. All right, what if, let me come down here and draw another picture here. What if we had a sample of size 15? Why is my pen not working? Well, now if we had a sample size 15, we're not going to work with a z distribution. We're going to work with a t distribution. In fact, we'd work with a t distribution with 14 degrees of freedom, n minus 1. If we wanted to use a two-tailed test, so let's say we have a not equal to test, and we have an alpha of 0.05. Now we're going to take that alpha and we're going to split it. We're going to put some on the left-hand tail and some on the right-hand tail. So the right-hand tail would have half that alpha. The left-hand tail would have the other half of the alpha. So I'd put 0.025 over here. And now we got to go and look up that value. Well, there's an inverse function in Excel. There's a t-distribution table. At alpha equal 0.05, we'd reject. When you go to that t-table, that inverse function, you get the value plus and minus 2.145. What we're saying is if the null hypothesis is true, we expect the test statistic to fall. That's what rejection regions do. We always specify, look at what it says, rejection regions, give values of the test statistic that are unexpected and lead us to reject. So I expect the value of the test statistic to be between the 2.145 and the negative 2.145. In the previous example, I expect the test statistic to be less than 1.645. But the rejection region always tells us when to reject. At alpha equal 0.05, we reject if. And then you have to fill in the blank. You have to come up with the z greater than 1.645 or the t greater than 2.145 or less than negative 2.145. How do you do it? You need a sampling distribution. You need to think, am I working with the z or the t? There's only two you're worried about now. Again, that'll grow, but you need to know what's the sampling distribution, what's the direction of the test, and what's our alpha. We need those three things. And once you have those three things, you know exactly how to come up with the cutoff points. This follows from everything we've done this semester. We've taken a look at sampling distributions. We know about z's, we know about t's, we know how to work with reliability, and so this is a natural step. If the null hypothesis is true, we know where it should fall. The rejection region tells us where it shouldn't fall, and that's when we're going to reject h naught. That's our first method of evaluating a test statistic. Oh, but wait, there's more. There is a second method. It's called the p-value method. And the p-value method is actually my preferred method. It's going to be your preferred method. It's the best way to make conclusions. And you're like, come on, let's go. Not yet. I'm going to hold off talking about p-values for a little while. What I've learned through the years is that if I give you too much, it gets confusing. So let's work with rejection regions for a little bit. Let's do some work. Let's work with tests for mean. Let's work with some large sample tests. Let's work with some small sample tests for a population mean. And then let's go ahead and take a look at the rejection regions. Okay, so we'll do that approach. Let's get that one down really, really well. And then I'll come back and talk about p-values. And I'll show you how p-values are related to rejection regions. Point is, there are 4 steps in a test hypothesis, and I like to joke that I'll teach you all 5 of them. There's 2 ways to evaluate a test statistic. The p-values I'm going to cover later. All right, so that's how we evaluate a test statistic. For now, all you're responsible for is rejection regions. We'll come back and we'll talk about p-values. So where we're at right now is the first step is identifying the test. We know what it is we're trying to do. We know the null and the alternative hypothesis. We've specified them, mu's equal to 50 versus the alternative mu's greater than 50. We go out and we collect some data. The sample data gives us a test statistic that's going to help us evaluate which of those 2 alternative, or the null and the alternative, is correct. That's step 2, the test statistic. And now we have a way of evaluating the test statistic. We're going to look at a rejection region. And so the last step, which is usually the easiest step, actually, from my seat, I get frustrated when you do the first 3 steps right and you screw up the 4th step, the conclusion. The 4th step is putting it all together, and I'm going to make you wait. I'm going to do that in the next video. So until then, get working on some rejection regions. So long.